to start this, post-break session with Alex Millar. He's now in Stockholm and is going to talk about alpha. And so a plasma Haloscope is quite exciting. So please, Alex, take the stage.
Thanks so much. To get started, I'm going to also have to give some credit to the idea to Eduardo, who is also one of the authors of the original papers. But basically, I'm going to be talking about a new detection mechanism for axions and dark photons. So I skipped the normal kind of introduction to dark matter slides just because I think we've already had a significant amount of motivation for axions and ultralight dark matter in the previous talks. So the coupling that we're going to be looking at exploiting heavily today is actually the coupling of the axion to photons. So this is not as novel as the axion piezoelectric effect. This is a very standard kind of coupling. The axion, or an axion-like particle, will kind of generically have some anomalous coupling to QED. So that looks like the axion coupled to FF joule, which you can also think of that as just E dot B. So if you have E dot B, you have a coupling to the axion. So this is kind of nice for the QCD axion because it's almost a one-parameter theory. So once you set the axion's decay constant, that tells you what the axion's mass is, and it tells you what this coupling is to the photon, up to some order 1 number, which is basically just telling you something about the high energy details of the theory. So essentially what's running through this loop in this triangle diagram. To put this in kind of a cleaner picture, it's much easier to look at just the axion Maxwell equations. So if you apply some external magnetic field, so you imagine you supply one of these photons virtually, that essentially induces a mixing between the axion and the photon. So you get these new terms appearing on the right-hand side of Maxwell's equations, some new source terms. The axion, if it's dark matter, has a very small velocity. So the main term that affects things is a kind of a current term that appears on the right-hand side of Ampere's law. So this kind of fake current will source some small electric field. And the part that's kind of going to be interesting for this talk is the fact that this induced electric field is actually inversely proportional to the dielectric constant. Somebody who really wants to exploit this could look at the fact that if you try and send this dielectric constant to be as small as possible, then you would have a large electric field, and potentially you could measure this electric field. So sending the dielectric constant to 0 is another way of saying that you have something like a plasma, which is near its plasma frequency. So if you insert the dielectric constant for a plasma, what you essentially see is that on resonance, the real part of the dielectric function goes to 0. Another way of saying that is the axion has a mass and the photon normally doesn't have a mass. So you can't convert between the two very easily because you need to break translation invariance in order to provide momentum to the axion. However, if you give the photon a mass, then you can allow for resonant conversion between the two, even in an infinite medium, because you can match your dispersion relations. Now, unfortunately, you can't send the dielectric constant exactly to 0 because your plasma is always going to have some lifetime. It's always going to have some losses. So the quality factor for this resonance is going to be limited by essentially the lifetime of the plasmon, which is this gamma factor. So that's kind of talking about some infinite picture. Unfortunately, we don't really have infinite plasmas in strong magnetic fields on Earth. If we want to build some experiment, we need some kind of finite sample. And the easiest case to solve mathematically is just that of a cylinder. So if you imagine you have some finite cylinder, you can write down Maxwell's equations with a lot of symmetries, and that makes it very easy to write down analytic solutions. In this case, we're going to assume that the magnetic field is aligned with the cylinder. You need to have some kind of boundary conditions. If I'm imagining I'm putting this inside a magnet, a cylindrical magnet is usually a solenoid. So we're going to assume that there's some conductive walls as a boundary. And then you can solve Maxwell's equations, and you get some term which looks like this infinite media term, and then some extra Bessel functions, which are telling you something about the walls of your vessel, or essentially, the radius of the cylinder. So this seemed maybe a little bit complicated, but pictorially, it's actually fairly straightforward. So the behavior of this system essentially just depends on how good your plasma is, so what the quality factor is, and then the relative size of your system. So if your system is really, really, really big, it essentially just looks like an infinite medium. So you see this red curve here, where you have a very, very flat response. So essentially, you get this infinite medium electric field that's being generated throughout the system. If your system starts interacting with the walls, so that's essentially what you see, these bumps here. As you go to higher and higher quality factors, essentially everywhere is within reach of the walls. So you get a shape that looks more like a traditional cavity mode. So this is, in this case, a Bessel function. So you get these kind of different regimes of behavior depending on the relative size of your system. So it goes between being something which is kind of like an infinite medium to something that operates kind of like cavity modes with, kind of interesting spatial features. So this is, just to kind of convince you that, if you do have an axion interacting with the plasma, you will get an enhanced detectable signal potentially. But what would you actually want in a material in order to make use of this? So, like in many of the previous examples of experiments, you really want a low noise system. I've told you that this electric field is enhanced, but it's still a very small electric field. You need to enhance this by a significant amount, but also have really nice low noise electronics in order to make some sense of this signal. So you can't have the when I say plasma, you tend to think, oh, this is some kind of hot gas. That's not the kind of plasma you want. You want something which is capable of operating in cryogenic temperatures. We don't actually know what the mass of the axion is. And because this resonance occurs when you match the mass of the axion with the plasma frequency, you need to be able to change your plasma frequency in order to measure different axion masses. In order to have a detectable signal, you also want to have a large volume. You want this plasma, because this entire effect is related to the lifetime of the plasma, you want this to be a very low loss system. And also you want the plasma frequencies to be relatively low. An example of a cryogenic plasma is something just like a metal. So if you take a piece of metal that's going to have a plasma frequency, and it's going to operate perfectly fine at cryogenic temperatures, but its plasma frequency is going to be more like electron volts. And the kind of frequencies we want to look at for kind of well-motivated axions is really more in the kind of the gigahertz regime. And while that seems like a fairly long laundry list, you can actually make materials that have these properties. So instead of finding a natural material that's going to have them, you can make your own. So this is something called a metamaterial. And It turns out one of the simplest versions of a metamaterial actually has all of these properties. So a wire metamaterial is really just a bunch of wires which are smaller than the wavelength of light. Because plasma frequencies are basically just determined by the electron number density and the electron mass, it actually turns out that the system modifies both of them. So the number density, it seems fairly obvious. You know, you just took out a bunch of material compared to a regular metal. So that's going to have less electrons, so you're going to have a smaller plasma frequency. But it turns out that you also change the effective electron mass. So if I imagine I'm trying to move an electron in one of these wires, it's going to create a little bit of a magnetic field. And that magnetic field is going to cause some mutual inductance with one of the adjacent wires. And it's going to mean that if I try and move this electron, it's also going to move this electron. So it's individually harder to move electrons. And this mutual inductance is really what gives you some collective oscillation, which makes the material behave like an effective medium rather than just a bunch of wires. So between these different factors, it turns out the properties of this material don't really care about the type of material very much. It's really just geometry. So if you have something like centimeter spaced wires, you're going to get something like gigahertz plasma frequencies. This can also be modified quite nicely. Because it's all geometry, if you modify this geometry, you get significant tuning. So for example, this is a plot showing that if you keep if you imagine moving from a square array of wires, so this was, you know, A apart in one direction and A apart in another direction, and you go to a rectangular shape, which would be A apart one direction and B apart in another. By changing this other direction, you can actually tune significantly the plasma frequency. And you can do other things like changing the distance between pairs of wires and things like that. So anything which changes this mutual inductance is going to cause a change in your plasma frequency. So there are kind of relatively simple one-dimensional ways to tune this system. There are also some kind of interesting behaviors. So if you want to have an experiment, you also need to have some kind of way of reading out a signal. It turns out that the amount of kind of area you can read out a signal from is limited in the system. So if you go to the plasma frequency, you go to essentially having the real part of your dielectric function going to 0. So the dielectric function becomes purely imaginary. So the refractive index has an equal part in its real and imaginary components. So what that means is at the plasma frequency, your system's going to be close to evanescent. So it's going to decay relatively rapidly. And that decay length is going to be something like the square root of the quality factor. So if you have a regime like I kind of showed before, where essentially your system is much larger than a square root of the quality factor times the Compton wavelength, you would need to have multiple antennas acting together in order to read out the full signal. Because if you imagine I have an antenna on one side, it's not going to be able to take energy away from something on the other side because it's going to have a decay length, more than a decay length away, I mean. However, if you are in this high quality factor regime, where your system size is smaller than this kind of square root quality factor, it turns out that you have a single moded excitation like a cavity, and you can read that out with a single antenna. So this is kind of an interesting design choice. You can kind of go bigger at the cost of adding more antennas, or you can restrict your size and have an easier readout. To give some sense of scale of these quality factors, in most cases, it turns out the dominant factor that comes into play is really just the resistive losses of the wires. Even if you have some kind of metal walls, there are a lot more wires compared to wall. So it turns out the wire losses are usually the most significant factor. And if you have relatively thick wires, it turns out that you can have quite high Qs. So even at room temperature, you can have Q in the thousands. And at cryogenic temperatures, you would expect that to go up by a factor of a few. So potentially Qs of 10,000 at cryogenic temperatures. So altogether, that means that a relatively large system, so this is the kind of the primary benefit of it, you can make something which would be, something like filling an MRI magnet, as opposed to a traditional cavity at this scale, which would be, a few centimeters large. So you can have a much larger volume. And that leads to a detectable signal at frequencies where traditional cavities are not really very effective. So you can see that this projection essentially moves above where traditional haloscopes are effective. For reference, this is assuming a Q of 5,000 and something like a 10 Tesla magnet with quantum limited detection. How am I going for time? So just very briefly, one kind of new experimental group that's looking to realize this is being called Alpha. So there's groups in St. Petersburg and Berkeley and Stockholm University, with also contributions from other universities, which are looking to kind of prototype and potentially build a plasma haloscope. So you can see here from some of the PhD students who've been working on this, different prototypes that have been trying to test different aspects of these material properties, and essentially make sure that we understand the systems that we're talking about. Apart from performing kind of detailed numerical simulations and understanding some of these important factors like quality factor and tuning more precisely, we've also been comparing some of these early prototypes with the theory to kind of see that everything is working as expected. And in general, the agreement between them is quite good. These are kind of preliminary results, but both in free space, which is on the right-hand side, these are free space measurements with very thin wires, and enclosed in the cavity measurements with relatively thick wires, both seem to have fairly good agreement between the theoretical predictions and the actual experimental results. And in fact, even with fairly low quality brass, it seems like you can get a quality factor of order 1,000 at room temperature. This kind of mixing between axions and plasmons is a really interesting way to push into higher mass regimes, by kind of putting the emphasis on modifying the photon mass rather than doing something like building a bigger cavity. You essentially break this kind of tyranny of scaling, which causes traditional cavity haloscopes to be less effective. So this leads to very competitive sensitivity in the high mass regime. And Alpha has been quite active, especially during the pandemic, in trying to perform the basic research to realize towards a full experiment. Thank you.
Thanks a lot, Alex, for this very nice talk about this, what I find a very, very smart idea. So now it's time for question, actually. So if there is some question, please raise your hand. Otherwise, I will start, actually, because I have a couple of questions. Okay, Joachim, please.
Hi.
Now you are muted.
Yes,
yeah, I realized I'm still muted. Sorry.
Okay.
Yeah, thanks for this exciting talk about this exciting idea. I was wondering, when the axions in the dark matter halo, well, they are moving after all.
Yes.
Is that tiny shift in their energy, is that something that you can resolve? In other words, would it help to look at the axion wind with different orientations of the director, like of the detector, because the Earth rotates during the day, to see a modulation there? Just because sometimes you're moving into the wind, so you see a slightly larger axion energy, and sometimes you're moving with the wind, so the Doppler shift is smaller.
Yeah, so there have actually been a couple of studies on this. So one of the so there are kind of two effects you can look for. One of them is just looking at essentially the speed distribution. So for a lot of these experiments, you have extremely precise frequency resolution. So you can imagine if you're looking for a kind of a Maxwellian line shape, the fact that that Maxwellian is shifting slightly can be detected. That creates quite a lot of data, so you're not going to use that to improve your sensitivity, but it will provide you some information about the dark matter halo. This does become sensitive to the axion wind more directly if it's larger than about 20% of a Compton wavelength. Sorry, a de Broglie wavelength. So you can imagine, the axion's phase is going to change essentially 100% over the course of a de Broglie wavelength. So if you have different parts of the device which are talking to each other, and they start getting far enough apart that the phase changes, then that leads to a change in the power in your system. So something like that is detectable if you start getting to very large devices. It's probably not going to help you in terms of a detection, just from the point of view that it's an added complexity to it. So I'm not sure if it necessarily will give you a lot of extra signal power, but it gets you a lot of extra measurement power once you have a signal. Mm-hmm. So the thing with these experiments, these scanning experiments, is that they're very, the hard part is the scanning. Once you see a potential signal, you can sit on that and get lots of data very quickly.
Also, you said you require a 20% change in the de Broglie wavelength, and that, well, we're not moving around the sun fast enough for that.
So yeah, no. So you, it's more about the it's not a 20% change in the de Broglie wavelength. It's when the experiment size is above about 20%, which is the de Broglie wavelength.
Okay. Sorry, I misunderstood.
So, basically, that's the point in which you start needing to really worry about the power variations in trying to make some of these like limit plots and things like this. It starts going to change it by a 20%, 30% level effect on the power. Mm-hmm. So you can detect it when it's smaller than that, but that's the point where it starts really changing if you're going to be able to, understand your experiment or not. Mm-hmm. But I don't think that will necessarily help you in making a detection, but it's a really great avenue for understanding more about the dark matter halo. So you can basically build up some, velocity map of the local dark matter, and that tells you something about the halo distribution as a whole.
Mm-hmm. Okay, very cool. Thank you.
Okay, any other question for Alex? Okay, in the meanwhile, some shy people show up. I actually have one, a very stupid one. But for example, in your plot, the exclusion plot, let's say, the limit on the right hand that determines the plasma frequency and is it an hard cutoff in the sense that you reach already the larger density that you can experimentally reach, or you can shift it a bit?
No, it's not a hard cutoff. I mean, so generally speaking, there are a number of factors that go against you as you try and go into higher frequencies. So you have higher losses because essentially the skin effect, the resistivities of high frequencies is worse than at low frequencies. So you're going to generically have smaller quality factors. You're going to have harder detector technology. If you look at this kind of a plot, if I go up to really high frequencies, like above, 0.1 eV and above, you can make really fantastic single photon counters. If I go to lower frequencies, like 10⁻⁵ electron volts, you can make really fantastic linear amplifiers. If you start going, around milli-electron volt, both of those are really hard. So your detector technology starts becoming a problem. So that starts becoming a problem even above about 20 or 30 gigahertz. You have worse detector technology. And then if you're tuning mechanically, you have more mechanical problems. you need higher tolerances and all this kind of stuff. So there are challenges pushing higher, but it's not a hard limit. It's just, you start needing kind of newer detector technology or better magnets and things like that to really make it as efficient as at lower frequencies.
Okay, I see. Thanks. So any further question? Okay, Julia?
Yes, hi, let me just get a video. Can you see me, or is it just a blue screen?
It's just a black screen. Yeah. Now we see you. Okay, go ahead, please.
Yes, I have a follow-up question on the question whether you can resolve the halo velocity distribution.
Yes.
So in conventional cavity haloscopes, up to now, I understand that the quality factor is always less than the dark matter Axiom quality factor. So when you calculate the power that you can extract from the cavity, you always kind of neglect the Axiom quality factor and say, oh, it's basically like a delta function. So how I was wondering actually today how, when people say that you can resolve the line shape, how you would actually do that.
So
if
the
cavity quality factor is worse than the dark matter one.
So that's a great question. So if you look at actually this plot kind of helps. So something like the quality factor, that's basically just telling you at a certain frequency how much is my signal getting boosted. It's not telling you the width of the signal you will see. So if I hit that, if I hit a cavity with a super narrow band or a mono frequency exciter, it's not going to broaden out into being multiple frequencies. So the quality factor doesn't smear the input signal. So if the Axiom's higher quality factor than the cavity, it's not going to be degraded into being a wider signal. It's just not going to get as boosted as much because essentially it can't keep ringing up the cavity more than a quality factor number of cycles. So because of that, you still have a very, very narrow signal, and the frequency resolution of these systems is actually determined by the bandwidth of the readout system and the measurement time. You need a certain amount of measurement time to get a certain bandwidth, but these bandwidths are very, very good. So in principle, you can have very, very fine frequency resolution even for a very low Q system.
Okay, so the thing I need to compare the Axiom quality factor to is the bandwidth of my readout, not the cavity itself. And so as long as that is very good, I can still resolve the line shape, just small in hand. Okay, perfect.
Exactly.
Thank you.
No worries.
Okay, fantastic. So if there are no other questions, I think that we can thank Alex again.